So now that we have discussed the layered networks in the abstract, now it's time to look at some examples. So now we are going to discuss two important network architecture reference model. One is the OSI reference model and other one the TCP or IP reference model. Then what is the difference between OSI reference model and TCP IP reference model? To understand this better, so let me explain about molecular theorem or gas mechanics. So in gas mechanics, what we have is you will have an ideal gas. What is an ideal gas? Ideal gas is the one which exactly follows the law PV is equals to nRT. Pressure times volume is equals to number of molecules times universal gas constant times temperature. If that exactly follows that law, no, actually there is no gas that exactly follows that law. So that's why if anything exists such a way, that's called an ideal gas. So if anything that behaves close to this PV is equals to nRT, also we can say ideal gas, but there is no such gas. That's why it is just ideal. It is just ideal, it doesn't exist. Whereas a real gases, there will be huge difference when you do the calculation pressure times volume is equals to nRT. So that's the reason we have ideal gas and then a real gases. So real gases doesn't follow the PV is equals to nRT. Similarly, if you come to the fluid mechanics, in fluid mechanics also we'll have an ideal fluid and then a real fluid. Ideal fluid is the one which exactly follow the laws of mechanics, laws of fluid mechanics, whereas the real fluid, they basically doesn't exactly go hand in hand with the fluid mechanic laws. For example, if one law is applicable, then another law can be applicable directly. So that is the reason. So when you do the fluid mechanic calculation, there will be a lot of confusion. So I hope I don't want to enter into fluid mechanics now. Okay, so now you got the difference. An ideal gas and a real gas, an ideal fluid and the real fluid, and a reference model and an actual model. A reference model and an actual model. So reference model is the OSI reference model and then actual model is the TCP or IP reference model that we are actually applying to our systems. So what is a reference model or OSI? OSI is like an ideal model. So we prefer to have these many layers, and this is like a reference, and whatever model that you want to build after that should should at least have these many layers or can have lesser than this, but it should by and large should follow this reference model. It's like a reference, it's like a reference to the a real model, like ideal gas, real gas, ideal fluid, a real fluid. Similarly, a reference model and an actual model. OSI reference model is the ideal one, and TCP or IP reference model is the actual model. So although the protocols associated with OSI model are not used anymore, so the model itself is actually quite general and still valid, and the features discussed at each layer are still very important. So the TCP or IP model has the opposite properties. The model itself is not of much use, but the protocols are widely used. For this reason, we will look at both of them in detail. Also, sometimes you can learn more from failures than from successes. So, OSI reference model and then TCP IP reference model. So, now let's, of course, there are plenty of other network models also, but we are going to discuss this. So the OSI reference model is the standard one, which is started first, and after that there were a lot of models that were built. Now let's begin with the OSI reference model. The OSI model, basically minus the physical medium, is based on a proposal developed by International Standards Organization ISO as a first step toward international standardization of the protocols used in the various layers. It was revised in 1995 day 1995. So the model is called ISO OSI. OSI means Open System Interconnection Reference Model, because it deals with connecting open systems, that is systems that are open for communication with the other systems. So we will just call the OSI model in short. So OSI model is nothing but Open Systems Interconnection Reference Model. So the OSI model has 7 layers. The principles that were applied to arrive at the 7 layers can be briefly summarized as follows. The first principle is a layer should be created where a different abstraction is needed, and each layer should perform a well defined function. And third, the function of each layer should be chosen with an eye toward defining internationally standardized protocols. And the fourth, the layer boundaries should be chosen to minimize the information flow across the interfaces. And the fifth, the number of layers should be large enough that distinct functions need not be thrown together in the same layer out of the necessity, and small enough that the architecture does not become unwieldy. So note that the OSI model itself is not a network architecture, because it does not specify the exact services and protocols to be used in each layer. It just tells what each layer should do. However, ISO has also produced standards for all the layers, although these are not part of the reference model itself. So each one has been published as a separate international standard. So the model is widely used, although the associated protocols have been long forgotten. So what will we do is, as we know, this is an ideal model and this is a reference model, and these protocols that belongs to this model have have been forgotten, have been lost, forgotten completely. So have been long forgotten before only. So that's the reason. Let's but still exploring and expounding the each layer of this model will give you a complete 360 degrees 360 degrees view on reference models. Then it would be very easy to understand the TCP or IP model. So that's the reason we are going to explore each and every layer of OSI, that's Open System Interconnection Reference Model. So how many layers it consists of? 7 layers. The application is the first layer, then data from application goes to the presentation layer, and application will have application protocol. Then layer number 6 is presentation layer. From presentation layer it will go to the session layer, that is layer number 5, and session layer holds session protocol. Then from session layer it goes to the transport layer, and transport layer number is layer number 4, and it holds a transport protocol. Then from there data travels to network layer, and network layer number is layer number 3, and it holds the most important, the actual hardware starts here. Through this network layer, a communication subnet boundary. Basically this network layer is communication subnet boundary. Then one network will be connected with the other network through the communication subnet boundary. And then the next layer that we have is data link layer. It's the layer number 2, and at the data link layer we will have a data link architecture. So this data links basically connect each other, and finally it enters the layer number 1, the physical layer. So the physical layer, it's nothing but transmission lines and then routers. So it both sides, host A and host B, both is going to have this one. So this the overall, the three layers: network, data link, physical layers, protocol, we call it as a internal subnet protocol. So, and the whole stuff we call it as a network layer and host router protocol. So only in the network layer we will have a host router protocol, and inside each will have a internal subnet protocol. But actually from network layer the actual hardware starts, the subnet starts, and then data links, and then physical layers such as router, and then transmission lines comes into the picture. So these are the seven layers OSI, open system interconnection reference model consists of. So now let us try to understand each and every layer of reference model, of OSI reference model. We'll begin with the first layer, that is layer 1. I'll begin with the layer 1. That is the physical layer. Then what is the physical layer? Okay, so the physical layer is concerned with transmitting raw bits over a communication channel. So the design issues have to do with making sure that when one side sends a 1 bit, so this is the name of the unit exchanged, name of the unit that will be exchanged, that is bit at the physical layer. When one side, that's a host A side, sends when a host A side sends a 1 bit, it is received by the other side as 1 bit, not as 0 bit. So typical questions here are: what electrical signals should be used to represent a 1 and a 0? How many nanoseconds a bit lasts, whether transmission may proceed simultaneously in both directions, how the initial connection is established, and how it is torn down when both sides are finished. So how many pins network connector has and what each pin is used for. So these design issues largely deal with mechanical, electrical, and timing interfaces, as well as the physical transmission medium which lies below the physical layer. So then we will move on to, basically this is the physical layer. Here we'll have physical layer host router protocol here in next, and then we will move on to the layer 2, layer number 2, that is the data link layer. The main task of the data link layer is to transform a raw transform a raw transmission facility into a line that appears free of undetected transmission errors. It does so by masking the real errors so the network layer does not see them. So it accomplishes this task by having the sender break up the input data, whatever input data that comes, that will be broken up into data frames. Typically a data frame is equivalent to typically a few hundred or a few thousand bytes, and transmit the frames sequentially. So if the service is reliable, the receiver conforms correct, because we have discussed so many types of services in our previous slides. If the service is a reliable type, the receiver conforms the correct receipt of each frame by sending back an acknowledgement frame. So here the unit is frames. So you can see Here bits, it's basically zeros and ones, but one level up it is frames. Frames will can have either few hundred or few thousand bytes. It could be 100 or 1000 bytes. Okay, so then we'll have the third layer, layer number 3, that is the network layer. The network layer controls the operation of the subnet. That's what I'm saying. The physical hardware starts. A key design issue is determining how packets are routed from source to destination. So, routes can be based on static tables that are wired into the network and rarely changed, or more often, they can be updated automatically to avoid failed components. So, they can also be determined at the start of each conversation. For example, a terminal session such as login to a remote machine. Finally, they can be highly dynamic, being determined a new for each packet to reflect the current workload. So when a packet has to travel from one network to another to get to its destination, many problems can arise. The addressing used the addressing used by the second network may be different from that used by the first one. So the second one may not accept the packet at all because it is too large. So the protocols may differ and so on. It is up to the network layer to overcome all these problems to allow the heterogeneous networks to be interconnected. So here the data is in packets. The name of unit exchanged is packet. So after that we will move on to the fourth layer, that is the transport layer. The basic function of the transport layer is to accept data from above layer and split it up into smaller units if need, so and then pass these to the network layer and ensure that the pieces all arrive correctly at the other end. So furthermore, all this must be done efficiently in a way that isolates the upper layers from the inevitable changes in the hardware technology over the course of time. So the basic function of the transport layer is to accept the data from the above layer and then split it up into smaller units and then pass it to the network layer, and also to ensure all the pieces have arrived correctly. So here, so transport layer, the unit is TPD, transport data units, a TPD. So it's a transport protocol. So this one is going to break up your data and so for that, so based on time, based on some other the sender name, based on the address, based on these factors, it will break up the complete message and it will attach in a headers, and then it will pass that to the network layer and the network layer will convert that into packets. Okay, so then we have the fifth layer, that is a session layer. So the session layer allows users on different missions to establish sessions between them. So sessions offer various services include dialogue control, keeping track of all turn. It is to transmit token management, preventing two parties from attempting the same critical operation simultaneously, and synchronization, checkpointing long transmission allow them to pick up from where they left off in the event of a crash or subsequent recovery. It's a session protocol DU. So that's what the SP DU. So then it's basically takes care of the sessions, and after that what we have is the layer number 6 is the presentation layer. The presentation layer, unlike the lower layers which are mostly concerned with moving bits of data around, the presentation layer is concerned with the syntax and semantics of the information transmitted. In order to make it possible for computers with different internal data representations to communicate, the data structures to be exchanged can be defined in an abstract way along with a standard encoding to be used on the wire. So the presentation layer manages these abstract data structures and allows higher level data structures to be defined and exchanged. So here we'll have a presentation protocol, PPDU as the name of unit exchanged. And then the last but not the least, layer number 7, the application layer. The application layer contains a variety of protocols that are commonly needed by users. One widely used application protocol is HTTP, that is Hypertext Transfer Protocol, which is the basis of the World Wide Web, WWW. So when a browser wants a web page, it sends the name of the page it wants to the server hosting the page using HTTP. So the server then sends the page back. Other application protocols are used for file transfer, electronic mail, and network news. So before we move on to the analogy, so I just want to I just want to give a quick summary about the reference model. That's OSI reference model. So application layer is the one which presents the message. If you take the WhatsApp example or mail, if you take the mail, whatever you see on the screen, that is taken care by the application layer. And then we have a presentation layer. Presentation layer is the one which converts the English language into basically another protocol that we use. If it is HTML protocol, if HTML language, if it is something else, then once it's been converted into that, now based on the sessions, the data will be broken into different pieces in the transport layer. Once it's been broken into different pieces in the transport layer, and then each of that message body has been given with the headers, and then that headers and then message body will go to the network in packets, and then these packets will be further broken into frames. That frame can be 1000 bytes or can be 100 byte or can be 1000 bytes. Then after that, these frames will finally split it into bits, zeros and ones, and these zeros and ones will be converted into basically a light signal in optic fiber, and it travels across the optic fiber, across the seas and across the continents, and finally goes to the physical layer, goes to the data link of the other side of the host B mission, and then same repeats, and it will become converted into frame and then packets and then TPDU and then SPDU, and then it will convert into HTML, and then HTML will be converted into English message that we can see and read on your computer.